Hello everyone and welcome back to the another class of fundamentals of particle and fluid solid processing, and we were discussing about particle size enlargement. Over the last 3 lectures we have seen its necessity, its mechanism. Particularly we are focusing on the granulation. Granulation, as we have mentioned, is the aggregation of smaller particles by agitation. Now we have seen different stages in granulation, or the different rate processes that actually dictates this granulation rate. So this we covered in the last class. Now just to give an overview what we have covered here, the schematic shows that the 3 rate processes that we discussed in the last class, and we are actually now focusing on the details of each and every step. So the first step was the weighting and nucleation. So that means when we have a bed of fine particles, the liquid binder, when it is sprayed or spilled over this bed of smaller particles, it should form the bridges. Now in order to do that, it should penetrate through that bed, and while doing so it has to weight the surfaces of the particles. Now that happens at this weighting stage. So this schematic, the first stage shows that the liquid drops are falling, or say in a single liquid drop here is falling on the surface of very small particles, and then it weights, it forms the bridges in between particle, and one granule is prepared or generated. Now this one granule, in the next state, in the consolidation and coalescence step, this granule consolidates itself, and that happens either by coalescing with the other granule or the coating with the smaller particles or the origin particles. So that leads to its consolidation and coalescence, and at the end this consolidated granule undergoes attrition and consequential breakage if the bonding by the bridges it's not sufficient to withstand that external force. So it creates small structures, stable structures or stable clusters. So that stage is the attrition and breakage, and this happens due to the movement of the particles in the granulator, due to the granulator movement, which induces the movement in the particle. So these particles are colliding against each other, granules are colliding against each other, it hits the solid surface of the equipment, that is the granulator, and by doing so this attrition and the breakage happens. And once after this, say, critical stage, the size remains more or less unaltered. So which means we can have a size distribution of the end granules or the end product. So now we are going into the details of the particular process or the rate stage, that is the weighting. So we have mentioned this terminology. One is the nucleation, which is the initial process of combining several smaller particles or the primary solid particles with a liquid drop. This is the point we say the nucleation has happened and the nucleus or the single granule has been formed. It coalesces, the sticking together of this granule with another granule or the granule and the primary particles. This happens, and basically combination of these processes determines the property of the end granules or the final product. Now, the granule size is basically limited by this competing mechanism of all these three rate steps that we have seen, that is the weighting and the nucleation, then we have coalescence, before that we had consolidation, and it is followed by attrition and breakage. So, competing mechanism of all these, or the interplay of all these three phenomena, dictates the final granule size. Now, weighting, if we now dig into the details, this weighting phenomena, it is nothing but the replacement of the air which actually fills the voids in between particles by the liquid binder, or the solvent containing liquid binder. Now, poor weighting means the chances are there will be ungranulated material, because the liquid bridges are not formed due to the absence of liquid in those pores, or say the surface weighting of the particles. If the liquid binder is not present on the surface, it is not binding the particles together. So, which means these ungranulated particles have to be recycled again for the efficient operation. Now, the cases where we have multiple particles or multiple materials we are combining into a mixture, there all these materials will have their own weighting properties. So, those properties has to be considered when we do this kind of combining several materials into a compact form. So, this weighting is governed by the liquid surface tension and the contact angle of the liquid with the solid surface or the particle surface, and this is a very important step in granulation, because the rate at which this weighting happens, it dictates how the granulation procedure will be followed. And a measure of such assessment has been done by Washburn, and Washburn equation says that assuming insignificant effect of gravity in that bed of small particles, this penetration rate, the droplet, it drops on the surface, as I mentioned earlier, it has to penetrate that depth of the small particles in order to fill in the pores of the interparticle gap. Now, this penetration rate, that is here, where Z is the penetration distance of the liquid into the powder, you can think of that is the bed depth which the droplet travels, the liquid binder droplet travels, is basically this expression. So, where this all the parameters, some of the known parameters or easily identified parameters are the viscosity mu, and theta is the dynamic contact angle. We have surface tension as well. Rp stands for the average pore radius, and that is related to the packing orientation, packing structure, packing density, or the size distribution of the powder. So, it is depends on the size of the small particles or the finer particles, that dictates this average pore size in between particles. So, this expression shows that this weighting rate or the penetration rate here is actually controlled by three major parameters. One is the adhesive tension, this parameter. Then we have viscosity, and the other thing is depending on the particle size, which basically dictates the packing orientation, size distribution or the packing density. All these things basically depends on the finer particle size or the origin particle sizes, that is making the cluster of particles or the size enlargement. So, these are the controlling factors in understanding the weighting behavior of the materials. So, this wash burn test requires some specialized equipment, specific instrument to measure this rate or the depth that it penetrates, because it is difficult in usual circumstances. As an alternative to this test or this quantitative measurement, there is a test called the drop penetration time test, where a very small droplet of known volume is gently placed onto a small powder bed of known porosity, and this method directly relates the weighting of the spray drops. So, here what happens, a drop of small volume of known volume is placed onto the surface of small particles or the origin particles of a bed of that particles of known porosity or voidage, and then the time taken to completely sink or absorb this droplet into this bed of origin particles is measured, and that has been shown as a relation of this expression, where Tp is the drop penetration time. All other parameters I have mentioned that this is the volume of the droplet, viscosity of the liquid, the bed voidage, this R we have seen as the pore radius, average pore radius, and this is the adhesive tension. So, this apparently is more easier to conduct in with the usual lab equipments. Now, in general, improved weighting is beneficial in granulation, because improved weighting provides us narrower granule size distribution in the product, and it also gives us better product quality control throughout the whole process. If we have better weighting, which means it is beneficial for the granulation, and the rate of weighting influences the extent of weighting as well, which is very critical when there is simultaneous evaporation during the granulation step. So, at the rate at which the liquid binder or the solvent is spreading over the small particles and its extent of weighting, these are two related, and this is more of a critical in nature when we have simultaneous evaporation of the solvent in order to make the bonds more stronger by replacing the liquids. In that case, this rate of weighting is a dominant factor in the granulation. Now, we would like to have the increased weighting, because we have mentioned that the improved weighting is beneficial. So, increase in the rate of weighting can be achieved by several ways. One is by reducing the viscosity of the droplet or say the liquid phase, because the highly viscous liquids are difficult to flow or spread over the particle surfaces. So, it has been seen that if you reduce the viscosity, the rate of weighting increases. Quite naturally, if we increase the surface tension, we can have the increased rate of wetting, minimizing the contact angle. It can spread over the particle surfaces very efficiently, and increasing the size of pores within the powder so that it can quickly penetrate, because as larger the pores will be, the liquid can penetrate easily into those gaps. Now, viscosity of this solvent depends on the binder concentration and the operating temperature. Now, it has been seen that with evaporation, binder viscosity increases because the concentration is changing, it is becoming more and more concentrated. So, the viscosity changes or increases during the evaporation step. The pore size, which is the particle related or depends on the different material of the particles that is made of. So, it depends on the particle and powder size, and wider distribution results in small pores. If we have wider size distribution of the particles, we can find smaller pores. Now, bigger particle will provide us bigger pores, smaller particles will be more compact during the packing, so it will provide us smaller pores. Now, this larger pores definitely enhances the rate of liquid penetration, but it provides lower extent of wetting. Along with these criteria, we have droplet size and the overall distribution of liquid. These are the other two vital parameters that dictates the granulation process, and particularly the wetting step. Because say one droplet usually generates one granule, and its size is proportional to that of the drop size. So, this droplet and its distribution, so the size of the droplet and its size distribution during its spraying or pouring over the bed of particles, that is one of the critical factor. So, during atomization, which means when we flow this binders, the solvent including binders, we spray over the bed of particles with a very fine droplets, we have to specifically must take a balance between the rate of this incoming fluid drops and the rate at which it is penetrating the powder, its ability to penetrate the powder, and the removal of wetted section from the spray zone or near the spray zone. So, we are basically spraying or atomizing say the liquid solvent including the binder over this small particle bed. Now, the rate at which we are pouring in this liquid droplets over the surfaces of these smaller particles, there should be a balance between this rate and the rate at which the droplet can penetrate, because it shouldn't form a pool of liquid at the top, that before it penetrates again another droplet comes on the surface of the small particles, because ideally each droplet should settle on the powder without touching each other, and it should sink very fast. Then the number of granules or the number of nucleus formations becomes larger in number or higher in higher. Such ideal conditions are called the drop controlled nucleation regime. That means each droplet is creating one granule, and each droplet when it sinks, it is not touching the other droplet, or its effect in creating one granule is not destroyed by the presence of other one. Such ideal case or ideal regime is mentioned or identified as drop controlled nucleation regime. Now, this happens at low penetration time, that means it should sink fast and at a very low flask. Now, that flask rate is basically proposed in a dimensionless value or number, which is expressed in this form, where Q is the solution flow rate, Vs is the powder velocity in the spray zone, droplet diameter or the average droplet diameter is dD, Ws is the width of the spray. So, this dimensionless spray flask basically provides a measure of density of drops that is falling onto the powder surface. If its value is much lesser than 1, then one drop wouldn't overlap with another and can form a separate nucleus granule. So, means the process efficiency becomes higher, that each and every droplet and its effect is not destroyed or hampered by the presence of other liquid droplet. At high flask rate, there is significant overlap of drops that results in much larger nuclei granules, and their size then would not be a simple function of the droplet diameter or the droplet size, because earlier I have mentioned that in this droplet control regime, where one droplet should ideally form one granule and the granule size is dependent on the droplet size. So, for in case of high flask scenario, this simple function would not be there. So, at a given flask value, the fraction of the powder surface weighted by spray drops has been proposed to be of this expression. So, if this is known, the flask rate is known, we can estimate the fraction of this powder surface that would be weighted, and the fraction of nuclei, the number formed by n number of drops, can be estimated by this expression. So, one hand we can estimate the powder surface area that is being weighted and the number of nucleuses, the granules that has been formed, that also can be estimated by a certain number of drops. So, basically this spray flask is helpful in scale up operation or scale up design of a certain granulator, which helps us to provide an initial estimate or initial guess on the nuclei sites or the sizes. So, when one combines this drop penetration time and high flask, it forms a regime map, nucleation regime map. That means in which scenario what kind of nucleation would take place, which factor will be dominant, that kind of scenario we say the regime map. Like we had one regime as the droplet controlled nucleation, and that happens, we have seen, at a very low penetration time and of a very low flask. So, such flow regime can be derived from the knowledge that we have seen, where we can see there are three regimes or three zones of nucleation. One is the droplet controlled, which we have discussed, we have seen what should be ideally in that scenario, that it appears in the low value of the flask and a very fast penetration time. So, the drop can penetrate completely before the new drop comes. This is the ideal case, that is called the droplet drop controlled nucleation site or the nucleation regime. The other one is called the shear controlled mechanism, where there is a domination of powder mixing and shear characteristics, and due to slow penetration, droplet coalescence increases. Before it sinks, another drop comes. So, the drop coalescence occurs and we have a broad nuclei size distribution, because that now bigger drop in generic, if we consider now that is also a isolated scenario, that bigger drop would create a bigger granule, and wherever that droplet coalescence is not happening, there a single droplet would create a nucleus as per its size. So, that means we have a variation in size distribution, and that is a broader size distribution. Now, the binder dispersion happens here by shear and agitation, and in between these we have the intermediate zone. So, here we have a narrower size distribution. In the mechanical case, in the mechanical dispersion regime or say the shear controlled regime, we have the broader size distribution. And then comes the granule consolidation state. So, weighting is done. Now, if we look at the granule consolidation, this granules that has been created by this weighting, this increase in the granule density resulting from the closer packing of primary particles due to removal of liquid through collisions is what the granule consolidation, and this can occur only during the state when the binder is still in the liquid state, because that liquid can escape and it can be compacted or consolidated. This consolidation step basically determines the porosity and density of the final granule. But this consolidation rate and its degree is controlled by particle size, size distribution, and the binder viscosity. So, the involved granule, its size, its distribution, and the binder viscosity dictates the rate of consolidation and the degree of consolidation. So, granule saturation, if that is defined as the fraction of pore space filled with the liquid, is controlled by two factors. One is the granule porosity and the liquid level, and this is the relation. From which we can see that with increasing porosity, saturation decreases, or with decreasing porosity, saturation increases. So, which means by changing one of these parameters or these parameters, we can control the granule saturation, which in turn helps us in having the compact size or the compactness or the consolidation of the granules. But beyond 100% saturation, this liquid comes up to the surface. It causes weighting of the surfaces, and that dramatically changes the granule growth rate, which we will see in the growth mechanism in the next class. So, in the next class we will see this growth mechanisms, how it is influenced by its controlling factors and what are the controlling factors, and we will see a couple of industrial granulator and its schematic and its overview. Until then, I thank you for your attention and we will see you in the next class.